Okay, so the next topic is about Cartesian products. Cartesian products. So definition and given, again, two sets. Let's start with two sets. Let's say A and B. The Cartesian product of A and B denoted by A cross B is the set of all pairs of the form A comma B with A belongs to A and B belongs to B. Okay, so A cross B means all pairs of the form A and B where the first coordinate comes from the first set and the second coordinate comes from the second set. So mathematically, in other words, A cross B, so all pairs of the form A and B, where A belongs to A, B belongs to B. Similarly, let's say if you have n sets, given n sets, let's say A1 to AN, and we can define, A1 cross A2 cross all the way to AN as the set of all n tuples this time of the form A1 to AN, where A1 belongs to A1 and all the way to AN belongs to AN. Okay, so this is for two sets, this is for n sets. The definitions are similar. Now example, let's say A equals 1 and 2, B equals, let's say 5. Then if you want to find A cross B, so all the pairs of the form A and B, the first coordinate comes from the first set, second coordinate from the second set. So I will have 1 and 5 and 2 and 5. So in general, so as you can see here, if A has, for example, 2 elements, B has 1 element, then A cross B has 2 elements. Now, what would be the general rule, do you think? So exercise. Suppose that, let's say A has n elements and B has m elements. Show that A cross B has how many elements, do you think? M times n elements. So in this example, 2 elements and 1 element, and the product had 2 times 1, which is 2 elements. Now another example, let's say A equals 5, empty set, and B equals 5 and 6. Then what do you think in this case A cross B would be? If A is empty set, B is 5 and 6, A cross B, but we have to look at the definition. All the pairs of the form A and B, where A comes from the first set. but first set is empty set, has no element in it. So in A cross B, that means I will have no pair, because if I want to have any pair, the first coordinate must come from the first set A, but A has no element. So that means A cross B is empty set. Because there is no element A and B, with A comes from the first set A, which is the empty set. And this is also consistent with this rule that I mentioned here as an exercise, that A times A cross B must have M times N elements. Here A is empty set, so it has 0 element. B has 2 elements. And then A cross B must have 0 times 2, which is 0 element. Okay. Yeah, so that's all about the first section. Now let's look at the second section, 2.2, set operations. Okay, now in this section, we have two sets, at least two sets, and we want to define a new set using an operation between them. So whenever we talk about operation in mathematics, it's performed between two elements of the same type. For example, addition is an operation that is performed between two real numbers, for example. And then you get a new real number. So similarly for sets, if I have two sets, I can perform an operation between them, right? So let's say we have different types of operations. I think you're familiar with them, like union, intersection, set difference, right? To get a new set. So I'm sure you're familiar with these operations, but let's remind ourselves about the definitions. The first operation we want to look at is union. So how can I define union of two sets? So given two sets A and B, we define A union B as the set of all elements that are in A or in B, or both. So remember, or what we call it disjunction in chapter 1 means when you say P or Q, when can I say it's true? If at least one of P or Q is true. If both of them are true, then of course I can still say that the whole statement is true. So when we say the elements that are in A or in B, that means they are either in A, just in A, or just in B, or in both. Because that's what the meaning of or is. But just to emphasize, I also mentioned or both. So for example, let's say A equals 1 and 5, B equals 2 and 3, then A union B would be equal to 1, 2, 3, 5. So the set of all elements that are either in A or in B or in both. All right. Now mathematical, say equivalent definition of union. So we can also define union with the language that we learned in chapter 1 for in logic, you know, conjunction, disjunction. So we saw that disjunction, because here in definition we had or, right? So from the logical perspective, or means disjunction. So I can say A union B is a set of all elements X such that X is in A, X belongs to A, disjunction, X belongs to B. Okay, and with Venn diagram, so that's with the logical language of logic. And then with Venn diagram, how can I show A union B? So see, again, we have two arbitrary sets. Let's say A here and here B. And then A union B would mean that, you know, all elements that are at least in one of them. So that means all these elements here. A union B. Okay. Now let's look at intersection. So again, given two sets, A and B, A intersection B is the set of all elements that are both in A and in B. In other words, the set of common elements. The set of common elements in A and B is called A intersection B and is denoted with this notation A intersection B. So equivalent definition again. So if I want to use the language of logic, A intersection B is the set of all elements X such that X belongs to A and also in B. And means what? Means conjunction, right? So conjunction X belongs to B. And with Venn diagram, how can I show the intersection? Again, see, I have two sets, A here, B here. And then A intersection B means the set of all common elements. So these are the common elements. Okay, and then let's look at an example. Let's say A equals 1 and 3, B equals 1 and 4. So what are the common elements between 1 and 3 and 1 and 4? There's only one common element, which is 1. Okay, now disjoint sets when we say that two sets are disjoint, so we say that A and B are disjoint if A intersection B is equal to the empty set. What about, so that's for two sets. For example, let's say A equals 1 and 3 and B equals 2 and 4 are disjoint since A intersection B is empty set. So that's for two sets. But if I have more than two sets, how can I define disjoint sets? So also, given, let's say, n sets, A1 to AN, we say A1 to AN are pairwise disjoint this time. If AI intersection with AJ is equal to empty set for I not equal to J, and of course I and J both between 1 to N. So if any two of them, that any two distinct sets that I consider, they have empty intersection, then I call them pairwise disjoints. If I have only two sets, then they're called disjoint if they have empty intersection. But for more than two, I have to get empty set for any two distinct sets. Okay, now what is the important property of this, disjoint sets or a pairwise disjoint sets? So let's look at an important property. So if A and B are pairwise, are disjoint, and finite, then cardinality of A union B is equal to cardinality of A plus cardinality of B. If A and B have no common element, disjoint means no common element, then when you take the union, the number of elements in the union is same as number of elements in A plus number of elements in B. I think we did an example here. See, for example, here 1 and 5 and 2 and 3. A had 2 elements, B also had 2 elements. When I took the union had 4 elements because A and B had no common element. Now we have a similar property for the pairwise disjoint sets. So again, similarly, I can say if A1 to AN are pairwise disjoints, and finite, of course, then A1 union to AN is equal to number of elements in A1 plus all the way to number of elements in AN. So the number of elements in the union is simply addition of number of elements as long as the sets are disjoint or pairwise disjoint for more than 2 elements. But what about if the sets are not a disjoint or pairwise disjoint? So remark, one can generalize rules above to arbitrary sets and the result is called the principle of inclusion exclusion. So let's see how it works. So for 2 sets, A and B, I can say the number of elements in A union B is equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. For two sets, number of elements in union, if arbitrary sets, of course. If the intersection is empty, number of elements in union is just number of elements in A plus number of elements in B. But in the arbitrary case, general case, number of elements in union is number of elements in A plus number of elements in B minus number of elements in the intersection. Why should I subtract the number of elements in the intersection? Because if there are some common elements, right? So in the union, those common elements appear only once, right? So for example, let's say if A is 1 and 3, B is 1 and 5. In the union, I would have 1 and 3 and 5. So 1 will appear only once. But when I add number of elements in A with number of elements in B, those common elements will be counted twice, right? One time they will be counted because they are in A. Another time they will be counted because they're in B. So in the left-hand side, A union B, we have to count them only once. But in cardinality A plus cardinality B, we are counting them twice. So what should we do? We have to subtract it with number of elements in the intersection so that one of those two counts will cancel. So we'll get rid of that additional count and we'll be left with counting every element only once, as we should. So again, the right-hand side, number of elements A plus number of elements B counts counts the common elements twice, one time as part of A, one time as part of B. We subtract with the number of elements in the intersection so that we count every element only once. So this is for two sets, and for n sets, number of elements in A1 union AN is equal to number of elements in A1 plus number of elements in AN. Then we have to subtract A1 intersection A2 A3 and all the way to AN minus 1 intersection AN. So we have to again exclude. So that's what is called principle of inclusion exclusion. So we have to exclude the intersection of any two sets. But then we have to again include three of them, intersection of three sets. Okay, and then the last term will be minus 1 to power n, let's say plus 1, A1 intersection to AN. So basically the idea here is that, for counting number of elements in the union of n sets, if we just add the number of elements, then we are counting some type of element more than once. So we have to subtract with the second group, but then again, we are subtracting too much. And therefore we have to again add some of them. So in other words, some of them are not even counted once. So we have to add with the elements in the third group and so on. And again, subtract with the elements of fourth group. And at the end, how can I find out about the last term, like justify it, or at least guess it, what the last term is? Well, if you look at the case for two sets, A and B, so it's number of elements in A and plus number of elements in B minus number of elements in the intersection. So for two sets, I will need minus sign. So if I include minus 1 to power n, minus 1 to power n, when n is 2 will be plus, not minus. So that's why I used minus 1 to power n plus 1, or you can say n minus 1, doesn't matter. So that for n equals 2, you get minus sign, and therefore this formula becomes consistent with this formula. So I'm not providing a proof for this. So this is called principle of inclusion exclusion. But I'm just saying, you know, there are ways to convince ourselves why this has to be true, and also find out about the pattern from what we observed for the case of two sets. So for this one, however, for the principle of inclusion exclusion, so you will see it in math. You'll see this formula. This formula and its applications in math 221. So if you take discrete math 2, you will see about the this formula again, and also its applications. Okay, now let's look at the definition for set difference. Set difference. So what is the definition? Again, we need two sets. Given two sets, A and B, we define A minus B. So the notation is like this: A minus A with a slash, and then B as the set of all elements that are in A but not in B. Okay, so A minus B is the set of all x values such that x belongs to A and x does not belong to B. Okay. Now let's look at an example. Let's say A equals 1, 3, 5. B equals 1 and 2. Then A minus B will be all elements which are in A but not in B. But for example, 1 is the first element in A, but 1 is also in B. So I should not include 1. But the next element of A is 3. 3 is in A, not in B. So 3 will be included in the set difference. Also 5 will be included in the set difference. And also with Venn diagram, what will be the Venn diagram for the set difference? So again, let's say this is A, this is B. A minus B means the elements that are in A, but not in B. So there are two types of elements in A. The elements which are in B, which means the common elements, which means the points of intersection. So we should not include those for the set difference. We should include only the elements that are in A, but they are not in B. So these elements basically. Okay. And then the next topic we want to look at is complement of a set. Complement of a set. Okay, for complement of a set, let's assume we have a set A. So given a set A, and we also need a universal set and a universal set U. We define a complement as the set of all elements which are in U but not in A. So A complement is equal to set of all elements X such that X belongs to U and X does not belong to A. So what is a universal set here? What do we mean by universal set? So remark, universal set is the set containing all elements in the context. For example, when A is a set whose elements are numbers, the universal set can be considered as real numbers. Universal set is a set that contains every element in the context. So when we talk about numbers, for example, integers or rational numbers, well, all these numbers are part of real numbers. So universal set can be all real numbers. When we talk about, let's say, people, let's say Canadians, for example, or Americans, then we can consider the universal set as the set of all people in the world, because all Canadians or all Americans are all a part of the set of people in the world. Okay, so when we have a set A, the A complement of a set denoted by A bar is the set of all elements which are, of course, in A U, because every element is automatically in U. So that's not the important part. The important part is the part that says that all elements in U which are not in A. All elements that are in U which are not in A is called A complement. So let's look at the Venn diagram. So before the Venn diagram, first of all, according to the definition we provided, A complement can be written as U minus A. According to definitions above. And the set difference between two sets A minus B is the set of all elements which are in A, not in B. Now for A complement, we said set of all elements which are in U, not in A. Therefore, A complement can be written as U minus A. So the Venn diagram here, how would it look like, the Venn diagram? So let's say if we have a set A U here, and then A here, then A complement would be all elements which are in U, not in A. So for example, let's say let's say A equals 0 to infinity, the interval. So what is A complement? Find A complement. Well, here we said, when we talk about numbers, we can consider a universal set to be set of real numbers. unless it's specified otherwise. But right now we can assume universal says all real numbers. So 0 to infinity means all numbers bigger than 0. So this is my original set A. Now what would be A complement? The elements which are not in A. Which elements are not in A? So from the real line, you can see it, right? So anything less than 0 will not be in A. What about 0 itself? Well, because 0 itself is in A complement, we should not include 0. But if 0 was not in A, then in A complement, we would have included 0 itself. Okay, so A complement would be equal to minus infinity to 0. Elements that are not in A. All right. So let me leave also an important property as exercise. Show that A minus B is same as A intersection B complement. Complement here we denoted with bar. So A minus B means what? Means the set of elements which are in A and not in B. Well, it's almost obvious why these two sets are equal, right? A intersection B is also the set of elements which are in A. Intersection means and in B complement, elements that are in A and in B complement. And in B complement means what? Means and not in B, because anything in B complement is not in B. So both left-hand side and right-hand side are the elements that are in A and not in B. So this is basically the intuitive reason why these two sets are equal. But how can we formally prove that two sets are equal to each other? Like here, A minus B and A intersection B complement. So I explained why, intuitively why they have to be equal, but how can we prove it formally? Let's say in exam, you want to prove formally that these two sets are equal. How can we do that? So for proof method for questions of this type, see below. I'll give you some examples how we can prove identities. So set identities. Set. So there is a table in your book about set identities, page 136. So please take a look at this table, but let's list few of them because we want to prove few of them. So one is, the one that we mentioned, let me repeat one more time. A minus B is equal to A intersection B complement. Two, A intersection with universal set is A, and A union empty set is A. These are called identity laws. And then we have domination laws, which says A union universal set is universal set. A intersection empty set is empty set. So these are called domination laws. In domination. And then we have commutative, which is A intersection B, same as B intersection A, and also A union B is same as B union A. And then we have associative law, which says A intersection B intersection C is same as A intersection B intersection C, and also for union, A union B union C is same as A union B union C. And then we have distributive law, and distributive laws, A intersection B union C is same as A intersection B union A intersection C, and also A union B intersection C is same as A union B intersection A union C. And then we also have De Morgan's law. De Morgan's laws, basically. So this one says, A intersection B complement is A complement union B complement. A union B complement is A complement intersection B complement. And you also have absorption laws. Absorption laws, which says A intersection A union B is A union A intersection B is A. And complement laws. This one says A union A complement is U, and A intersection A complement is empty set. Let's look at the last one, for example. A union A complement means elements which are in A or in A complement. But every element in universal set is either in A or A complement, right? Because if an element in the universal set is not in A, then by definition it has to be in A complement, because A complement is a set of elements which are not in A. So that's why A union A complement is the whole universal set. But what about the intersection? Again, obviously intersection is empty set, because elements which are in A and A complement, so there's no element which is in both, because A complement is a set of elements which are not in A. So there's no element which is in A and also in A complement at the same time. So these are, however, this type of reasoning are called intuitive reasoning. They give ideas to us why these properties must hold, but they are not formal proofs. So in the exam, when I ask you such question, you are required to write a formal proof, a precise proof. How does a formal proof or precise proof would look like for this type of question? So proofs So let's do, for example, 8 A intersection A union B equals A. So let me give you a general recipe how we can prove an identity of this form. So to prove an identity of this form, you can prove that left-hand side is a subset of right-hand side, and right-hand side is a subset of left-hand side. This will imply that left-hand side must be equal to right-hand side. If you show that one set is subset of A is subset of B, and also B is a subset of A, then that means A and B must be equal to each other. So this is the common technique to prove set identities. We have to prove left-hand side is a subset of right-hand side is a subset of left-hand side. So let's see, for example, now for this one, we have to prove. So to prove now, to prove A intersection A union B equals A. So we said we have to prove two things: left-hand side subset of right-hand side is a subset of left-hand side. First, we prove left-hand side is a subset of right-hand side. Now, how do I show that one set is a subset of another? I have to take an arbitrary element in the first set and show that that element must be also in the second set. So let X belongs to let X belong to A intersection A union B. Then by definition of intersection, if I know that X is an intersection of two sets, it means it has to be inside both of those two sets. So then X belongs to A and X belongs to A union B. Well, there's a conjunction. So if there's a conjunction, that means both of them must be true, right? So that means in particular, X belongs to A. Right? If X is in A and in something else, it means both of them are true. So in particular, the first one is true. So X belongs to A. So that means X belongs to the right-hand side. That's it. I started from X from left-hand side. I showed that X has to be in the right-hand side as well. Now, to prove the other way around. So I have to show that A is a subset of A intersection A union B. So again, let X belong to the left-hand side, which is A. Then, so X belongs to A, because I just assume X belongs to A, so I'm just repeating it again. And X belongs to A union B. So note, if X belongs to A, then X belongs to A or X belongs to B. And so X belongs to A union B. See, look at this one. And this is my assumption. I'm assuming X belongs to A. I'm claiming that this will be true. But this part, now, if I want to show a conjunction is true, I have to show that both parts are true. But this part is obviously true because I just assumed it. Is my assumption. So I can say, of course, this is true because I just assumed it. Now this one is also true. Why is this one true? When can I say that this one is true? If X belongs to A or X belongs to B is true. If X belongs to A or X belongs to B is true, then I can say this is true. But this is true. Why? Because I'm assuming again, what was my assumption? X belongs to A. If X belongs to A is true, then this will be true. Why? Because there's disjunction between them. When can I say that the disjunction statement is true? If at least one of them is true. Well, I know that this one is true by my assumption. So this whole statement is true. And if this whole statement is true, that means X belongs to A union B. Why? Because by definition of union, A union B is the set of elements X for which this statement is true. But now I said this statement is true, so X belongs to A union B. So that's the justification of this part. And then that means X belongs to A intersection A union B. Because if this statement is true, that means X belongs to intersection of this set and this set. Well, that's it. Therefore, A intersection A union B equals A. Now let's look at another proof. Proof of, let's say De Morgan's law. Let's prove one of the De Morgan's laws. For example, A intersection B union intersection B complement is A complement union B complement. So let's see how we can prove this one. So again, same technique. I have to assume that X belongs to the left-hand side, show that X belongs to the right-hand side, and then one time X belongs to the right-hand side, show X belongs to the left-hand side. So first, suppose that X belongs to the left-hand side. Now, X belongs to a complement of a set. If X belongs to a complement of a set means X does not belong to the original set by definition of complement. Then X does not belong to A intersection B. Thus, so what can I say? So that means the negation of, right? X belongs to A intersection B is true. When can I say that X does not belong to A intersection B? If negation of X belongs to A intersection B is true. Because negation of X belongs to A intersection B is X does not belong to A intersection B. Now, what about this one? What does this one mean? When can I say X belongs to intersection of two sets? If X belongs to the first set and X belongs to the second set. But look at this one, negation of X belongs to A and X belongs to B. If you remember, we had an identity for this in chapter 1. Which that one we also called De Morgan's law. So that one was De Morgan law for logical statements. This one is De Morgan law for sets. So we are basically using the De Morgan law for logical statements to prove De Morgan law for sets. So this one, I can say from chapter 1, identities. We can say that this one, do you remember what is it? So this is negation X belongs to A or negation X belongs to B. Negation of P and Q is same as negation P or negation Q. Okay, now what is negation of X does not belong to A? Negation of X belongs to A is X does not belong to A or X does not belong to B. X does not belong to A is same as X belongs to A complement or X belongs to B complement. X does not belong to A means X belongs to A complement. And then this means X belongs to A complement union B complement. By the definition of union, right? When can I say that X belongs to union of two sets? If X belongs to the first set, disjunction, X belongs to the second set. So I started with X belongs to left-hand side, show that X belongs to the right-hand side. Now let's do the opposite. Now assume X belongs to A complement union B complement. I can basically reverse these statements, right? Just go from bottom to above, the steps are reversible. So I can say, X belongs to A complement union B complement. Then I can reverse the first step. So that means X belongs to A complement or X belongs to B complement. And then this means X does not belong to A or X does not belong to B. And then that means negation of X belongs to A or negation of X belongs to B is true. And then I again apply the chapter 1 identities, De Morgan law for logic from chapter 1. That means negation of X belongs to A and X belongs to B is true. That means X does not belong to A intersection B, right? And then that means X belongs to A intersection B complement, which is exactly what I wanted to show. So this was the proof of De Morgan's law because I showed that left-hand side is a subset of right-hand side. Right-hand side is a subset of left-hand side. So I proved 2 of these identities for you. You can prove the rest in a similar way. Any of these you want to show that left-hand side is a subset of right-hand side and right-hand side is a subset of left-hand side. How can you do that? Well, if you take one element, the left-hand side, show that it has to belong to right-hand side. Also, if X sum belongs to right-hand side, it has to belong to left-hand side. Well, that's all you need to do for every one of these properties. Okay, so proof of rest of properties. Proof of rest of properties exercise. Okay, guys, so these are some basics of set theory and some basic identities. And next time I'll also do some examples where we can prove some identities using these basic identities. So for proving any identity, of course, one way is to take elements, take element the left-hand side, show in the right-hand side show it in the left-hand side. For basic identities, which is this list, basically this is the only way. But for some other identities, we can also, prove them by using these basic identities. Of course, we can still prove them by taking elements, but we can also prove them by using these basic identities. Okay, so I'll show you some examples for this type of questions next time, and we'll also go over some generalization of a union and intersection. Let's say if we have union or intersection of infinitely many sets, how can we define those type of unions or intersections? Okay, guys, so thank you and see you next time.